Good morning, everyone, and welcome to today's Combiotes workshop. We are very happy to have you all here and look forward to a very engaging session. My name is Cristina Dincă. I'm the project manager of the Combiotes project, and today with me we have Arnaud Bruch from CA, the French Alternative Energies and Atomic Energy Commission. He's the coordinator of the Combiotes project, and we also have Xinjin from the Technical University of Denmark, which is another partner institution of the project. We are organizing this workshop as part of the project training activities. And before we begin, I would just like to inform you that the session will be recording, and I hope that everyone is comfortable with this. The recordings will be available later. I would also like at the beginning maybe to kindly ask you to quickly turn off your camera so we can take a screenshot, which will just be used for promotional purposes. So can you please do this for me very quickly?
Okay, so we can start.
Okay.
Just I will share my screen again. Okay, just is it working properly?
Yes, yeah, we can see it in the presentation mode.
So thank you everyone to be here. As mentioned by Cristina, my name is Arnaud Bruch and I am the coordinator of the Combiotes project. I'm working at CEA, the French research center for nuclear application and alternative energy application. Today this is a workshop about, we'll try to give an overview of the designing, the sizing of a specific PCM thermal energy storage for residential application. Just first, some elements about the Combiotes project. The Combiotes project is basically one of the last, or perhaps the last project in a H2020 call of European Commission. And the objective, the goals of this call was mainly focused on the development of core building, heating and cooling system, some thermal storage at for daily storage or interseasonal storage, some new materials, some innovative technology to try to perform load shifting, to reduce energy consumption, to increase the renewable energy, and to increase the efficiency of heating and cooling system. So it's quite large. Just regarding the Combiotes project, so it started at the end of 2019 and it will end at the end of this year. It's quite long just because the project has been suspended during a little bit less than 2 years due to the defection of a partner. The consortium is made of different partners and coming from 8 European countries, from Czech Republic, Denmark, from Poland, UK. We have also one Chinese partner for a specific demonstration. Just to give you an overview of the location, of the different partners. And I will say a few words about the context. What you can see here with the 2 figures, basically this is more or less the same stuff, but based on different sources. What you can see is for residential, for typical house, this is the consumption, as the typical consumption during a typical day. And so you have, for example, here the electricity consumption, and in blue, light and dark, you have the domestic hot water and the heating demands. On this graph, you have more or less the same with the consumption for domestic of hot water in orange, the total consumption for the house, and the PV production also, if you have PV on your roof. And so what you can see is that we have peaks of domestic hot water consumption, mainly in the morning and in the evening. We have some peaks of electricity demand, which are concomitant with this peak of domestic hot water consumption. In parallel, we have an important shift, a temporal shift between the PV profile production and this peak of consumption of electricity and thermal needs. So that means that we have an opportunity to contribute to the load shifting of the electrical grid, and we have also an opportunity to correct the mismatch between the PV production and the thermal needs by using thermal storage at residential scale. So the ComBioTES project, basically in ComBioTES, what we want to do is to develop thermal energy storage solution for thermal application in house. So for typically for space heating and or for hot tap water production and or for cooling at residential scale. What you can see here is the real scope of the project. So the main scope of the project will be the development, test, characterization, demonstration of two different thermal storages. One mainly, the first one called the versatile, mainly for heating and free cooling, and the second one, which is the topic of this workshop, for the production of domestic hot water and space heating. In parallel, in the project, we have an important task devoted to what is called EMS, Energy Management System. So TCMS is supposed to make the link between the grid, between the PV on the roof, between the cost of the electricity, between everything, basically, and the thermal storage and the thermal needs. The objective is to operate efficiently the thermal storages. If we go a little bit more in details for the concept, so we have these two thermal storages, and we consider a different way to operate these thermal storages. And basically, depending on the season, if we are in winter and if we are in summer. In winter, when the electricity price or the PV production are high, when the electricity price and the demand are low, we are considering to charge both TES. And when the demand and or the electricity price are high, we will discharge the thermal storage for space heating and or hot tap water. The behavior will be a little bit different in summer. With low price of electricity, we will make what we call a cold charge of the versatile TES that will be used later for cooling, and we will charge the PCM TES for domestic water. And when the electricity prices are high, or when we have a demand, we will discharge the versatile for space cooling, and we will discharge the PCM storage for hot water. This is the principle. Some objectives of the project will be quite short on this slide. So we have a lot of objectives, and the main objectives basically is to design, characterize, test both thermal storages, the versatile one and the PCM storage. We have to work on a new PCM, bio-based PCM for heating and tap water. We have to develop the EMS, the Energy Management System. We will perform some kind of techno-economic analysis and environmental impact also. And something which is a very important part of the project is the demonstration. And basically, the demonstration will be made in a lot of different sites. The first one, the main one, will be the CEA in Grenoble in France, because CEA is responsible for the development of both storages. So that means that we will test the versatile and the PCM storage from scientific point of view. Then we have a demonstration site in China to test the versatile TES. This is a scientific characterization, academic tests. And then we have three more realistic demo sites. The first one is at DTU in Denmark. We will test the PCM storage for space heating, in not a real house, but a close to real house. This is a representative house with a lot of different installation. We have at CEA in Chambéry, in France, we have the same kind of installation. We will test the PCM storage for space heating and hot tap water. And we have a site in Poland, which is a real house with real people inside, a 4 people family. And we will test the PCM storage in real condition to produce hot tap water. And so basically today the workshop will be divided in 4 different sessions. The first one will be focused on the input. So what are the specification, the requirement, the constraints for the dimension, for the sizing and the definition of the storage. In session 2, we will focus mainly on the protocol and the way the storage has been defined and the way we transform a storage into a complete prototype. In session 3, we will focus on the EMS, the energy management system, the architecture, the philosophy, and the different development, the use cases, and we will close the workshop with the session 4 and the demonstration, the demo sites, the way the prototype will be integrated, and the use cases. And so it was a short introduction. If you have any question, maybe we can start with the session 1 and then have the question on this introduction and the session 1 at the end of the first session. It is okay for everyone? Okay. So the input data. Basically, the first step will be to obtain enough data, enough elements to know what we want to size, basically, the specification and the requirements. So I put again some elements on just to summarize some elements of the ComBioTest project, and just to highlight the scope of the workshop. The workshop is only focused on the PCM storage and the EMS for thermal used in-house, for space heating, and for domestic hot water production. The scope of this workshop and the definition of the PCM storage is mainly to try to fulfill the load shifting for the electrical grid, at the same time to fulfill the use of the residential PV, and as I said, for domestic hot water and space heating. And so what we need at the end of this first session is to obtain figures about power, energy, temperature, specification for the material, and specification for the strategy and element for the EMS. So what we will do is to see some specification for the thermal storage according to the electricity market and according to economical aspects. At the same time, on the other end of the spectrum, we will see some specification according to the thermal used. Thermal uses, so this is the domestic hot water and space heating application. We will briefly look at some recommendation and specification regarding the PCM. Just PCM is for phase change material, so that means some specification for the material used in the thermal storage. And we will also look for some specification for the development of the EMS. The first element is the electricity market, since we try to participate to the grid load shifting. So we look at different regulation in Europe of the electricity market. It's not so easy. It's a little bit blurred. There's a lot of different regulation. And the main conclusion is that this is not easy because there's not a single and easy configuration. And basically, each country is a specific case. In addition, this case, this regulation should or may significantly evolve in the next years due to the evolution of the electricity market and the electricity business. And so that means that a full implementation of TES for load shifting will be linked with a lot of different configuration, a lot of different various models for energy storage. Just if we look more in details, we can consider or we can highlight that the main electricity tariff, depending on the country, could be categorized into a flat tariff. So that means that the price is the same all the time. What is called the time of use. So that means that the prices may change on different time period. For example, different with the season, different between night and day. We have what we call the critical peak pricing. So that means that we have some very high prices during very specific hour, in general, this is during the peak of consumption. And we have what is called the real-time pricing. And so that means this is a more or less a quasi-dynamic or a really dynamic evolution of the price of electricity. And this is mainly based on the electricity markets. The first thing that has been made in the project is to evaluate the relevancy of the power to it for thermal energy storage business, depending on the price tariff. So we choose different country. We have 1, 2, 3, 4, 5, 6, 7, little bit then less use cases, mainly in Europe, but including China also. And we try to evaluate the cost efficiency of thermal energy storage. For flat tariff, the main conclusion is that there's no interest because there's no difference in the prices between night and day, for example. And basically, when the prices of electricity are evolving with time, it is more and more interesting to use thermal storages to perform power to it. And obviously, the most interesting elements, the most interesting situation will be a real dynamic tariff of electricity. So just from electricity market point of view, we can say that this is basically what just I'm saying is that we need evolving price of electricity, even if maybe it's not the best solution for the simple consumer. And some of the different cases that we show in the previous slides will be integrated and considered for the EMS and for the evaluation of the relevancy from economic point of view of the thermal energy storage. If we look at the other hand of the spectrum, so the thermal uses, we look at first for the domestic hot water regulation. It's not so easy also because it's different in every country. It's not really regulation. It's more kind of list of strong recommendation. But it can be more or less summarized as it is. So you have a minimum temperature in the water tank because all these regulations are made for the water tank, which is the thermal storages deployed in houses. You have basically a maximum temperature, minimum and maximum temperature in water tank. You have also a minimum and maximum temperature in the draw-off. Based on this small review, it was possible to define some element for CombioTES. And basically, we consider that we want temperature higher than 60 degrees in CombioTES, and we will consider that the discharge will be stopped at 40 Celsius degrees. So we consider that temperature below 40 Celsius degrees is not usable, which is a classic configuration. If we look more deeply in the domestic hot water data, we can see that we have this kind of element. So what you see is a typical consumption of domestic hot water in-house in different countries, Poland, Denmark, France, China, Germany, as a function of time. So what we can see on this graph is that the curve in blue, which is France, is more or less a little bit different than the other. It's a little bit strange because we can see that we have a peak of consumption in the morning, a peak of consumption in the evening, but we have also some peak of consumption during the afternoon. If we accept this specific configuration, what we can see is that we have mainly a peak in the morning and a peak in the evening. So that means that we have to consider that the storage should be able to fulfill these two peaks. Regarding the typical value of consumption, it is possible to consider that we need the typical value for the sizing of the storage is that for a house of 4 people, we need something like 899 kilowatt hour of thermal storage for the production of domestic hot water. Just something to remind is that what you can see here is the typical electricity consumption of the same house in the same country, and you can see that there's a kind of concomitance of the peak of domestic hot water and the peak of electricity consumption. And this is even more true in the evening. So that means that from economic point of view, there's an opportunity for the business of thermal energy storage for the participation of grid load shifting and to try to make more money by not using electricity for the peak in the evening. If we look at the space heating regulation, it's even more blur and even more even less we have even less common behavior in Europe. Basically, for example, you can see here in Poland and in Denmark the typical heat demand for space heating for the different months of the year. You can see that in Poland, basically, the heat demand is almost constant over the whole day, and just we have some typical evolution depending of the months. In Denmark, it's quite different. We can see that we have a peak in the morning, a slight reduction in the afternoon, a second peak in the evening, and an important reduction after 10 p.m. So that means that it is not possible to define a single load profile. It will depend on the country. And in this case, also, we can see that due to the concomitance of the peak of space heating and peak of electricity consumption, for example, in Denmark, we can conclude that there's a kind of opportunity for TES to participate for grid of shifting linked with space heating. If we try to summarize the needs, we can conclude that basically for the PCM storage, something like 10 kilowatt hour for hot tap water and sometimes also for space heating can be sufficient to fulfill 100% of the daily use of the house. And so, based on these elements, we define the first use cases. So for domestic hot water, we want PCM with temperature higher than 55, 60 Celsius degrees. We want a storage with a capacity in discharge about 8-9 kilowatt hour at outlet temperature higher than 40 Celsius degrees. The thermal power in discharge will be a little bit higher than 20 kilowatt. This is taken from ADEME in France, which is the French Institute for Energy Used. And the typical discharge flow rate will be 12 liters per minute from ADEME also. For space heating application, due to the large diversity of configuration, we choose to use the the typical specification and typical configuration from the DTU partner in Denmark, because it seems to us that it is quite relevant. And so that means that the outlet temperature in the space heating, the inlet temperature in the space heating system will be 55 Celsius degrees. The return temperature will be 45 Celsius degrees, and the nominal flow rate is 13 liters per minute. Just you have to keep in mind that a storage size for domestic application will clearly be too small for complete space heating application, but it is not a problem. It is quite accepted in the project. Now that we have defined briefly the use cases, we have some recommendation specification for the choice of the PCM. Just from technical point of view, we want a bio-based PCM. We want a melting and solidification temperature quite in line with the use cases. Obviously, we want the highest possible volume enthalpy. Obviously, we want a high thermal stability. We want that the PCM will not have some oxidation, dehydratation. And it is quite preferable that there is no supercooling, because supercooling has to be managed, and in this case, it's not so easy. From economical point of view, it should be as low as possible, even if this is not the first order, because the price of the PCM is not the first element in the final price. And from safety point of view, we are looking from non-flammable, non-explosive, non-toxic PCM, and something that is clearly harmless for human and for environment. And now we can briefly speak about the specification for the EMS. What you can see here is basically the configuration considered. We have here the real thermal energy storage. Then we have a middle level layer, which is the PLC. So this is the process control, the monitoring of the PCM storage. And then at the bottom, we have VEMS. And so VEMS will exchange element with the PLC, receive the data from the TES, and the EMS should give some order to the PLC based on elements and based on data from the PCM, TES. And basically, as I said, the EMS, so it takes some data from the thermal storage and is sending element to the thermal storage as a response of this data and as a response of other configuration or other consideration. This consideration are mainly the one listed here. So obviously we have the end user. So that means that the end user is asking for space heating, asking for hot water. But we have to consider also the grid operator. The grid operator, for example, he can say that he would like to see a reduction of the load on the grid. We have the aggregator. If we consider that we are not only considering one single thermal energy storage, but we are considering that thermal storage can be controlled in mass to make a mass effect. And we have other consideration, for example, the weather forecast, this kind of element. And so for the EMS, we have this kind of specification. On the left, you can see the global geometry with the thermal storage, the PLC, with the EMS. We make a calculation between information and requirements coming from, as I said, the user, the grid, the price, the weather. At the same time, the EMS has to consider the feedback from the states of the thermal storage. And for the deployment of the EMS in the demo site, we have consider different scenarios. The first one is mainly based on the objective of reduction of costs, based on the price difference between on electricity between period on high prices and low prices. It is based on time of use tariff, and we will use some case based on France, Poland, UK, Spain, and a specific case for the Denmark, because Denmark is already using quasi-dynamic tariff. We have a second scenario based on the peak load reduction, which is mainly based on the France use case, because in France we have a specific time of use tariff, and we have a mostly nuclear production of electricity. So we are a very specific configuration for the production of electricity. And we have the final scenario, in which we will try to optimize the use of local renewable energy, which is mainly based on the demo site in Poland, because in the TES demo site we have also PV on the roof. And so we will consider two different specific cases, which are the net metering for the prosumer and the net billing. So if I try to summarize the specification, we want PCM, or we want temperature higher than 55 Celsius degrees inside the PCM. We want something like 8 to 9 kilowatt hour in discharge, with threshold temperature of 40 Celsius degrees and thermal power higher than 20 kilowatts in discharge. We have specification also on the thermal flow rates. T-specific calculation, T-specific requirement has been complete by some element for space heating. Mainly, we have changed the temperature, and the threshold of 40 Celsius degrees is now a threshold of 45. We have some simple and basic recommendation for the PCM. We have some recommendation based on the electricity market. So we want to perform electrical heating to participate to the electric grid load shifting. We want to be able to integrate local PV. And for the EMS, we have to consider a 3-level EMS from low to very high level of decision. And we have defined 3 typical use cases that will be tested and characterized on the different demo sites. And so, based on this different specification, we will see in the next session how this different requirement and specification will be considered to define and to size completely the thermal storage. Do you have any question, any remark? Christina, if there's no remark, do we just continue to the next session?
Yes, yeah.
Okay.
We can go ahead with the next session.
The next one is more technical. This is clearly frankly speaking, this is the sizing of the TES, which has mainly made at CA by my colleague, Bénédicte Champel, who is unfortunately not available today. But just I wanted to mention that this work was not made by me, but and so the sizing, the design of the PCM storage. Just to remind, we consider hot water and space heating. We consider PCM storage. We want electrical charge, and we write in the proposal that we wanted something higher than 100 kilowatt hour per cubic meter. This is the storage density. This is quite high. This is an objective. In this session, we will also present the transition from the paper design we perform at CA to the final design of the tank, integrating all the mechanical aspect, and we will also show you how we move from the tank design, the final tank design, to the complete prototype that we called music in the project. Music, it is for multi-pass storage with internal charge. Just I remind you once again the use cases. And the first step is to choose a geometry. At this step, we consider, frankly speaking, we consider a classical geometry. This is a tube and shell configuration. So we have a bundle of tubes. These tubes we are considering thin tubes from petrochemical industry. So that means that these tubes are easily available, can be easily found in different sizes, different configuration. In the tubes, we are including inserts to reduce the section, and so to increase the velocity and to increase the heat transfer coefficient on the water side. So this tube bundle is placed inside a shell. The shell is filled with PCM, and on the top and on the bottom we have the distribution, the plenum inlet and outlet, in which we will find the fluid distribution system. In the shell also we consider a gas volume, so that means that a part of the shell is not filled with PCM, just to be sure that the thermal dilatation between liquid and solid will be managed without any pressure issue. So to define this storage, what we need is to fix the geometry of the tank, to fix the geometry of the tube bundle, the number, the diameter, the fin characteristic. We have to check that everything is okay from hydraulic point of view, and we have to fix also the PCM. How it was made? It was made following basically this approach based in 5 different main steps. In the first step, we are considering some pair of tubes and inserts, and we will try to make a first selection based just on a purely energetic model. So that means that some element will be already excluded at the end of this step. At the end of this step, the remaining configuration will be simulated using a dynamic model to take into account all the physical phenomenon inside the tank. At the end of this step, we will assess also the flow regime inside the tube bundle. So it is laminar, it is turbulent, it is in transition. Are we in forced convection, natural convection, mixed convection? And the final step will be to evaluate the influence of different parameters to increase the efficiency of the design. This approach has been presented in a conference last year, and is currently an article will be submitted soon on this approach. So the first step, as I said, is a purely static energy consideration. So that means that we are just calculating the total energy that can be stored and discharged in a given geometry of thermal energy storage. And so the energy is calculated between an initial temperature, a final temperature, and integrating the sensible part of the energy and the latent part of the energy. We are considering the tubes, the inserts, the fins, the PCM, the water in the collector, the inertia of the tank wall, but we do not consider the storage in the dome end. We do not consider the thermal losses, and there are absolutely no consideration of the physics inside the tubes. So that means the thermohydraulic behavior. So we start with a first kind of pairs. We have some, for example, some TES pair as based on a tube diameter and insert diameter. So we have small tubes from diameter 25 to big tube of diameter 50. We have some diameter for the insert, and we are considering also the number of tubes. In this case, we are considering an array, a bundle based on triangular array. So that means that we are not putting the number of tubes we want. We are to following a rule. So we are considering basically this reconfiguration based on 7 tubes, 19 tubes, and 37 tubes. And so we are evaluating in this configuration the first geometry of the tank, diameter and height, to obtain the 8 kilowatt hour between 40 Celsius degrees and 70 Celsius degrees. So the first element is that, for example, all this configuration have been excluded, because what you can see here is the storage height as a function of the number of tubes for the different pairs. And in this configuration, the minimum height of the storage is 2 meters, from 2 to 4 meters, which is clearly not consistent with the requirements of thermal storage inside house. So that means at the end of the first stage, we are considering only this configuration, which are highlighted in green. Sorry. So this configuration has been then simulated using the dynamic model. This dynamic model has been already presented in detail in a publication, so you can find it here. And this dynamic model is, in a sense, quite simple. So that means that we have not so simple. The storage model is divided into a first volume, which is the top collector. At the bottom, we have another volume, which is the bottom collector. So we are simulating top and bottom collectors, and we are dividing the tube bundles into 2 separate parts, the one in the center and the one close to the wall. We consider this configuration because the tubes near the wall will see different elements, and mainly considering the thermal losses. And so it was more realistic to do like that. And this model has been integrated just in quite simple elements based on we have the thermal storage, and so we are putting inside temperature, mass flow rate, and we want at the outlet minimum temperature of 40 Celsius degrees. What we obtained is typically this kind of result. So this is evolution of temperature as a function of time, evolution of power, evolution of mass flow rates into the storage, and evolution of energy. And so what you can see, for example, is that the red curve is the temperature at the outlet of the storage, and the blue curve, the green curve is the mixing temperature. And so at the beginning, the temperature at the outlet of the storage is clearly higher than 40 Celsius degrees. So that means that we have to do a mixing between the inlet temperature and the outlet temperature of the storage. So that means that part of the flow rate is not sent to the storage. But with time, the outlet temperature of the storage is decreasing. So that means that more and more flow rate is sent to the storage, and less storage is bypassed. At a given time, this time, the mixing temperature is below 40 Celsius degrees. As you can see, that means that we can continue the discharge, but in our case, we consider that the discharge is over and the storage is considered empty. And if we consider this configuration, we can see that in this case, we have discharged something like 6 kilowatt hour. This is a problem. This is not 8 kilowatt hour. So that means that we do not fulfill the constraint of the specification of 8 kilowatt hour in discharge. That means that not all the energy charge has been efficiently discharged and not all the energy charge has been effectively used, which is the problem. So we try to look more deeply at the different configuration that are still considered. And for example, we have, for all this configuration, we have 8 kilowatt hour that has been stored between 40 and 70 Celsius degrees. And we can see that depending on the configuration, we have discharged only two a little bit less than 7 kilowatt hour. So we are able to define a kind of discharge efficiency, which is the ratio between the energy effectively discharged and the energy that has been charged previously. And so this efficiency is ranging from 28 to 85, which is quite different. So the first thing, the first conclusion is that in any case, we do not have 8 kilowatt hour in discharge. So we have to increase the height for all thermal storage, for all the configuration we have considered. And some of the configuration has been excluded also because we have to increase too significantly the height. And just at the end of this process, you can see in this case, this is the evolution of the discharge efficiency as the function of the tank height. We considered only 3 final configurations: design 1, design 2, and design 3. These designs are okay with all the constraints at the moment. Now we have to consider something which has not been integrated in the dynamic model. In the dynamic model, we make a huge assumption. We make the assumption that inside the tubes, the water is in forced convection. But this is something that has not been assessed at the moment. So we make this assessment. We consider the map flow of Eckert and Mette, which is a classical map flow of single phase flow in force, mixed, and free convection, including laminar, turbulent, and transition regime. And just we calculate the relevant numbers, the Reynolds numbers, the Grashof numbers, the Prandtl numbers. We put these numbers on the map, and what we can see is that the first design, the design 1, can be excluded also because the design 1 is at the same time in a mixed convection regime and in transition between laminar and turbulent. So that means that we are basically in non-so-stable flow. So it had been excluded. We have just remaining 2 design. And for the 2 design, we were just looking at the annular space inside the tube, so the space between the tubes and the inserts. And we can see that this annular space is ranging from 2.8 to 3.5 millimeter. And just based on the CA expertise on previous design, we are considering the design 2 with the maximum annular space just to try to avoid the cloaking. So we have a reference design, which is the design 2. This reference design is based on 37 tubes, 25 millimeter of outside diameter. We are using octadecanol with a melting temperature of 55 Celsius degrees. And in this case, we discharge effectively 8.2 kilowatt hour between 40 and 60 Celsius degrees with a discharge efficiency of 45 Celsius degrees, 54 Celsius degrees. So basically that means that a little bit less than half of the usable energy is not effectively used. So the next steps are to see how to improve this percentage. This is the sensibility and sensibility analysis. The first element we are looking for is the fin pitch. Just to show you, we have the tubes, we have in green the fins, and the fin pitch is the distance between the tubes. Obviously, if you increase the fin pitch, you will increase the mass of PCM, so you will increase the energy that can be stored, but you will increase mainly the mass of PCM in this zone, which is called the free PCM. So this is a zone that are outside the fins. So that means that it is a zone which is a zone of low thermal conductivity. So this is energy that may be difficult to be effectively discharged. So we make the analysis from a pitch between 20 millimeters to 1 millimeters. And what you can see is that if you decrease the pitch, you will significantly decrease the mass of PCM from 200 to 100. You will significantly decrease the energy effectively discharged from 9 to 7 kilowatt hour, but you will significantly increase the discharge efficiency to 45 to 66. So that means there's a kind of balance to obtain between the energy that can be stored and the energy that is effectively discharged. We test also the PCM and the charge temperature. On the two first columns, we consider the same PCM octadecanol, and just we increase the charge temperature from 70 to 75. The consequence is that we increase the discharge efficiency from 54 to 55. So the impact is quite small. On the contrary, we change the PCM. And for example, in this case, we use two different PCM with a melting temperature of 70 Celsius degrees. In this case, we increase drastically the discharge efficiency, and we reach something like 80 Celsius degrees. And basically, the interpretation is relatively easy, is that the threshold temperature is always kept at 40 Celsius degrees. If we increase the melting temperature of the PCM, we increase the parts of the latent heat that will be used. And so that means that we will increase, as a consequence, the discharge efficiency. And the final element that has been studied is the flow pattern. The classical way to design and to operate a PCM storage is to consider a single pass fluid flow. So that means that all the tubes see the same level temperature at the same time at the inlet. And in this study, we introduce what we call the three-pass fluid flow. So that means that at the first, the fluid is entering the tubes on the peripheral layer. Then it will leave this region and enter the second layer, this one. And finally, it will enter the tube on the center. We can consider also a three passes flow in the inverse direction. So we start with the inner tube, then the middle layer, and we finish with the peripheral configuration. And just as a theoretical approach, we considered what we call the 37 pass. So that means that all the tubes are connected in series. And we can consider that in this case that we have more or less only a single very long tube. We consider the exact same configuration of the storage in terms of temperature, diameter, and the consequence is that with a single pass, we have a discharge efficiency about 54 Celsius degrees. This discharge efficiency is increased to 70 and even 75 Celsius% in the three-pass flow, and in the 37-pass flow, we have an efficiency close to 100%. The interpretation made is that by increasing the number of passes, we are increasing the water flow. We are increasing the velocity of the water flow inside the tubes. So we are increasing the heat transfer coefficient. And so we are increasing the global coefficient between the water and the PCM. And by increasing this coefficient, we are globally increasing the efficiency of the exchange. And so we are able to discharge more efficiently the stored energy. The last thing that has been studied is the internal heating. Internal heating in PCM storage is not so easy. And so in this project, we consider that we will perform internal heating by adding some heater inside some tubes. So we perform some simulation with different number of tubes, different configuration of and position of heater, and different power. Just to make it short, we have selected the configuration in red based on a total of 3 kilowatts of heating, which is quite consistent with the typical power in water tank for the same application. We consider 7 tubes to obtain something which is more or less homogeneous or not so heterogeneous on a given plane. And using this configuration, we consider that it is possible to perform a full charge in less than 6 hours. And we consider that it is quite consistent with, for example, in France, with the heating during the night for using domestic water during the day. And so at the end of this process, we have our design with some backups, because we are not sure that everything will work properly. And so the design is basically based on what I have been present before. In this design, we have changed the PCM. This is now a paraffin with a melting temperature of 70 Celsius degrees. In this design, we are considering 3-pass flow. We are considering electrical heating with internal heater. And the expected performances is a discharge efficiency of 81%, which is quite roudoudou. We consider some backup. Just if it's from engineering point of view, it is too complicated, the internal heater will be removed. In this case, we can see that the discharge efficiency is a little bit higher than 100%. It can seem to be unlogical, but in fact, it can be easily explained just by the fact that this discharge efficiency is only based for with a threshold of temperature of 40 Celsius degrees. And so, in fact, during the discharge, we will use the PCM at temperature below 40 Celsius degrees to make the first step of the heating. So that means that part of the energy below 40 degrees is used to maintain temperature higher than 40 degrees. We have a second backup if it was not possible to make the 3-pass flow. So in this case, we are considering a single pass flow with electrical heating. In this case, the efficiency is 70 degrees. And the backup from the backup, that means it is a single pass flow without electrical heating. And in this case, we have an efficiency of 85 Celsius degrees. This value has been just calculated also for the second use cases, the space heating. And basically, this is more or less the same, with efficiency ranging from 73 to a little bit higher than 100%. So, as a conclusion, at the end of this process design, we have what we can call a kind of paper design. This is a design without any consideration of engineering, of feasibility, of complexity. But it is a design with 2 innovations, and the main one being the 3-pass hydraulic pattern. So the next step is the transformation of this paper design, which is this one, into a real design for the fabrication. And the conclusion is the transformation leads to this value, which is a 3D representation of the storage currently under manufacturing. Basically, what you can see is that, for example, we have this element, which is not included in the paper design. This element is made for the thermocouple installed inside the storage, because if we want to characterize finally the performances, we need some instrumentation. This instrumentation will be presented more in details later. We have also a lot of holes here to integrate a lot of sensor for the measurement of the state of charge. So all this transformation took more or less few months to be sure that everything is okay and everything is mechanically feasible. What is really interesting for us is that we made we made with success the integration of the 3-pass flow and the integration of the internal heating. Obviously, we will have to see if it works properly during the characterization phase, but just from engineering and manufacturing point of view, it is a success, it is made. In this project, we continue also with a final step, which is the transformation from a TES tank to a prototype. Because obviously, if we want to install the TES tank just as a classical water tank, the tank is enough. But in this situation, this is a research project, so we defined a music prototype in which a lot of components, a lot of sensor has been added, in which all the backups have been integrated also. So that means that we need to define a lot of circuits and elements, additional circuit and elements. And basically, you can see here, for example, just the PCM storage shown in the previous slides in the instrumentation. But we have to consider also a first part of the hydraulic circuits for the mass flow measurement, for some safety configuration, for expansion considerations, for measurement also. We have to consider also here some measurement of the flow rate also. And in blue, for example, we have here an additional circuit, which is the backup of the internal heating. If the internal heating is not working properly, we are adding this backup. So that means that the charge will be made using an external heater. Obviously, that means that from a single tank, we have a very big, heavy, and non-cost-effective prototype. But as said before, we are in a research project, and if we want to properly characterize the behavior of this prototype, we have to know the value of the flow rate, the value of the pressure, the value of the temperature, where it's working well, where it's not working well. So what you can see here, this prototype is currently under manufacturing. The tank is made for one prototype, and the skid will be finished in the next few weeks. So that means that the first prototype to be filled with PCM and to be tested may be finished in 2-3 weeks. And so at the end of this process, we consider that we have a fully operational prototype that can be tested on the demo site. Any comments? Any question?
Yes.
Yeah, there is a question. Go ahead.
Yep.
Gilles.
Yes, thank you for the presentation. Just one question about the PCM. At the beginning, the PCM is supposed to be a biobast. And at the end, do you think RT is a paraffin? Yes.
Yes.
Also, you think it's not possible to define a tank with PCM, which is very efficient and with biobased material?
But this is a bio-based paraffin.
Ah, it's a bio-based. Okay.
It's and just to give more information at the beginning, I did not mention it because it was too long, but RT70HC is our backup for the PCM. At the beginning, we wanted to try a new PCM, and we tried isosorbide, which is sugar alcohol. With the melting temperature in range with the application, we try this element because it was also a project manufactured by one of the partners in the project, but we just have a small issue, which is the supercooling. So before in parallel with the design process of the PCM, we put isosorbide in one of the CEA prototype and already existing prototype of PCM storage, and we perform some characterization. And the conclusion is that we have some supercooling at storage scale. So that means that we choose not to use this PCM, and we choose to use a backup and to not define or to not characterize a brand new PCM.
Okay, thank you.
Can I do just a comment? It's Fabrice Bentivolio from CEA. Just to say that RT PCM, so sold by a German company, Rubitherm, includes three kinds of PCM. Some of them have paraffins, some of them have fatty alcohol, and some of them are fatty acid. And RT70HC, it's a fatty alcohol. So that's why it's a bio-based PCM. It's not a paraffin.
Okay. Thank you.
Thank you for the answer.
Okay.
Okay. Are there any other questions?
Yes, Luc from Insula France. I was also interested in the PCM choice. So you mentioned octadecanol. Is it isosorbide, as you said, or is it different?
No. Nope. Octadecanol was our first choice because is a PCM which is, from safety point of view, is really good. From supercooling is really good. From previous experience at CEA, it was good also. From performances in terms of latent heat, it was good also. From melting temperature, at beginning, we were thinking it was good because it is about 55 Celsius degrees. But after the first element of sizing, the conclusion is that we in discharge we obtain only we discharge efficiently only half of the energy stored. So the PCM octadecanol, this is not isosorbide, and we change from octadecanol to RT70HC just because the melting temperature was too low, in fact.
Okay. Okay. Second question: do you have an idea of regarding the total heat of the storage? How much is, if you consider the water and the steel and the aluminum, how much does the latent heat represent? Is it 50%, 30%?
Yes, I do not have the exact number but if I'm not wrong, and Fabrice just say perhaps can help me if I'm wrong. What I have in mind is that basically latent heat is about half of the energy discharge.
Okay, fine, thank you.
And just keep in mind that in our application, we stop the discharge at 40 Celsius degrees. So that means that we are more focusing in the temperature range of the latent heat.
Yes.
All the V energy stored below 40 Celsius degrees is sensible heat, and we consider that this heat is not usable.
Okay, but we could still use it for space heating at low temperature.
Yes, and when you take your shower, when the temperature is below 40 degrees, you continue to take your shower.
Mm-hmm.
Just if you look at this, the green curve here, you see
Yes.
that the temperature is decreasing very
Slowly.
fast. So that means that between 40 Celsius degrees and 25, it will not take so much time.
Mm-hmm. Okay.
Okay, so maybe I can have one question because I think I didn't catch it properly. Why the higher melting temperature is beneficial when it concerns the discharging efficiency?
For our explanation is that when, for example, when you consider octadecanol with melting temperature of 55 Celsius degrees, so that means that you will during the discharge you will put inside the storage inlet temperature at about 12 Celsius degrees. The storage has been heated, for example, at 70 Celsius degrees, but from 70 to 55, this is sensible heat. So you will consume, or you will use this energy between 70 and 55 quite fast, because this is sensible heat. And then that means that the latent heat will be only discharged between 55 and 40 Celsius degrees. So that means that parts of the latent heat cannot be discharged, because you will stop the discharge before you have consumed or you have used all the latent heat. If you increase the PCM melting temperature, for example, to 70 Celsius degrees, the temperature difference between 40 and the melting temperature is higher. So that means that you will have not more time, but you will be more capable to take the energy of the melting temperature. I'm not sure if I'm quite. Is it okay for you?
Yes,
my explanation?
Perfect. Okay.
Thank you.
If there is another question, you can go again. You can go ahead, Gilles, and ask your question.
Okay, just a small compliment about the melting range. Do you have a slide to show between the different biomass material? Do you have to see more in detail, perhaps the difference?
We perform a kind of review. The term is a little big, too important. But I do not have a slide. Just I can give you some information between, and perhaps Fabrice can give more detailed information. But in the range between 50, 55 to 75, you can find different bio-based material. Not so much, but you can find different bio-based material. And if you remove the one with supercooling effect, if you remove the one with safety configuration, if you remove the one with some dehydration or segregation effects, you do not have so much choice.
Does the question is about the melting temperature range between the solidus and liquidus?
Yes.
Okay, so most of the PCM we have considered, we did a calorimeter measurement, and we can consider that it's a pure PCM all of them, and the melting range is around 2 Celsius degrees, no more.
Ah, it's very small. Okay.
Yeah, for octadecanol, for RT70HC, and for isosorbide for the tree, the melting range is very short.
Okay, thank you.
Sorry, I did not fully understand the question, and my answer
No,
was not
but-
the good one. Sorry.
But your answer was also interesting.
One question, please.
Yep.
Still Luc from Insula. If we regard the three-pass system, then it means that in the central part of the tank, you will have, did I say that? You will have melting at the same time at the top and at the bottom of the tank. Right?
You mean due to the fact that, for example, TES parts will see hot water, and then you will have hot water at the bottom of TES parts?
Yes.
This is something that will be studied, but what we think is that in this configuration, in fact, we have PCM with low thermal conductivity. And so we consider that basically between the different pieces, we may have some thermal exchange, but it will be more or less limited due to the low conductivity of the PCM. And so during the sizing, one assumption, the assumption made was that each pass can be more or less considered as independent. And during the scientific characterization, we will see how this assumption was good or not.
Okay. Because my concern was that you would have a melting starting at the bottom, and then a risk of the
mechanical failure. Yes.
For example. Yeah.
Yes, exactly. This is something that has been considered during the design. We think that it should be okay.
Okay.
But it is based mainly on our expertise and feeling, but we are not sure.
Okay. Well, it depends if there's a film of melted PCM all the way up.
And we are expecting that finally the liquid will always find a way to the gas volume on the top of the shell.
Okay, fine. Thank you.
Hi, I'm Xin, and now I will introduce the energy management system EMS part of this project. What is an EMS? An energy management system EMS is a framework for energy consumers, including the industrial, commercial, and public sector organizations to manage their energy use. And the primary goal of an EMS is to improve energy efficiency and reduce energy consumption by having real-time insights to energy performance and providing energy optimization, which leads to cost savings and environmental benefits. And many organizations adopt EMS as a part of their broader sustainability and corporate social responsibility initiatives. And the design and implementation of EMS are often determined by specific applications. For instance, there are EMS tailored for individual devices, such as the battery EMS, and designed for larger systems, such as the building EMS. And there are also some complex configurations, such as the EMS for the entire industrial park. And the EMS in this project, the Combiotis, is designed to achieve efficient energy management of the phase change material-based electrical thermal energy storage in households. And the figure 1 presents a typical envisioned fully integrated ETES that is installed in a building. And the whole system consists of 3 levels of processes. At the bottom level, the physical electrical thermal energy storage the TES exchanges electricity and heat power with electricity grid and thermal, such as using PLC, are implemented together with metering and sensoring equipment to conduct any predefined control logic, such as turning on or off a valve when temperature within the ETES reaches a certain level. And this level of process often involves a certain level of decision-making or control logic that has been built in the technology providers. And at the top level, an EMS is deployed to achieve efficient energy management with single or multiple service-oriented objectives, such as fulfilling a thermal load profile requested by the end users, and minimizing the electricity bills by charging or discharging the ETS smartly, and following a grid operator's request to provide demand response services. And the design and implementation of the EMS can vary from case to case, depending on the service scope and other relevant factors, such as the hardware platform, the software, and the communication protocol. And the COM-Beltis EMS has a relatively generic configuration, wherein communications take place between the EMS and other parts residing either inside or outside of the ETESS. And the figure 2 presents a relatively generic description of the EMS setup. And within the ET, communicate to the ETES unit by retrieving the operation data of the ETES continuously, and also sending an operation schedule or a control signal to the ETES continuously or event-based. And this requires the EMS to have a reliable communication with the process control solution and condition monitoring function implemented by the technology provider. And outside of the ETSS, the EMS need to provide communication interface with the following systems or the stakeholders, like from the end user, who may provide direct request of energy demand and settings, like turn on or turn off, or an indirect request of energy demand by pre-setting a temperature set point of space heating or domestic hot water in order to meet objectives. And for the energy supplier or the aggregator, who may want to control the ETS directly, such as by sending one or a series of energy power requests, or indirectly, such as by sending energy prices or energy consumption limits in order to meet objectives. And for the grid operator, who may want to control the ETS directly, such as by sending one or a series of energy power requests, or indirectly, such as by sending prices of different types of grid services in order to incentivize the end users' participation in demand response programs, in order to use the flexibility offered by the ETESS to support the grid operation. And others, such as the building smart home operators, who may want to integrate the ETESS into their portfolio, or just to provide additional information, such as the weather forecast, building demand estimation to support the operation of the ETESS. And the COM-Beltis EMS will be deployed and tested in 3 locations. First is Denmark for the space heating case, and France for the domestic hot water case, and also the Poland in a real house case. And in these three countries, the market framework and operation modes are different. So we designed 11 application cases, and which are classified into 3 scenarios. And they are used to specify the function needs, benchmark the performance of the COM-Beltis EMS based on the simulations and physical demonstrations. And for the first scenario, the goal is to achieve the operation cost reduction considering price difference, like the TOU tariff and the cost dynamic tariff. And for the second scenario, the goal is to achieve the peak load reduction using ETS flexibility. And for the third one is the optimal use of local renewable energy. And we take the first scenario, operation cost reduction, as an example. The decision making in the EMS is achieved by the economic model predictive control, which employs an economic related objective function for real-time control under complex and uncertain conditions. This implies a sequence of adjustments for manipulated variables computed and applied to keep the reference trajectory over a future time horizon. And the cost function is defined to measure the economic performance or sum of squared control errors predicted over some time horizon. And the minimum cost is guaranteed. And the EMS prototype built in this project integrates several key components to ensure optimal performance and energy efficiency. We can see from this figure 6, there are three key components. And for the first one is the PCM-based thermal storage system, the music. And the music system forms the foundation of the thermal storage, utilizing the internal and external heating elements or both to charge the system with heat, which is then supplied to the household. And this system includes the storage unit and the essential interfaces such as the electricity, heat, and the communication. And for the part 2, the household energy network. This part represents the household energy network, which delivers electricity to the music system and receives heat from it to fulfill the heating needs of the home, such as space heating and domestic hot water. And for the part 3 is the EMS part, and the integrated EM solution consists of a PLC here and the router and the EMS platform. The PLC is programmed to automate rule-based processes such as real-time control, data logging, and safety and protection based on local data from the music system. And in the event of a disconnection between the PLC and the EMS platform, the system also allows personnel to manually control or stop the operation of the music. And the router serves as a communication gateway, ensuring secure data exchange between the PLC and the EMS platform. It also enables the EMS to access global information channels, such as electricity prices, weather forecasts, and the flexibility service requests, and both locally and remotely. And for the EMS platform, it's designed to host and execute an intelligent module-based EMS that proactively optimizes and controls the operation of the music. It sends generation schedules to the PLC, where the router for execution continuously updating these schedules in real time. Additionally, the EMS can exchange information with external global data sources, further enhancing its ability to respond to various dynamic conditions. And given the different configurations of the music, like with the internal or external heating elements, or it's for space heating or domestic hot water, and also different operational conditions like the dynamic hourly pricing or the time of use tariffs. So each of the different EMS prototypes has slight differences tailored to the specific needs of the demonstration sites. And a mock-up of the final EMS has been developed to facilitate testing and evaluation while the music system is still under development. So as seen in the figure 7, it's an overview of the mock-up setup. And a PLC is programmed to automate the supervisory control and data acquisition processes. And the EMS is deployed on an industrial computer, referred to as the EMS PC. And the data exchange and the data exchange and integration are supported through the EDDK platform hosted by DTU. And EDDK provides open and real-time access to various data sources, such as the electricity processes, prices, weather forecasts, and weather conditions. And in this mock-up setup, the platform offers APIs as allow seamless data exchange between the EMS and relevant data channels. And a router acts as a communication gateway between the EMS PC and the EDDK platform, which can provide the smooth data transfer. And the communication between the different system components is established and tested for a preparation test. And to monitor the and control the system, a PLC system together the container where the instrument is housed was designed and deployed in our previous test. And as seen in the figure 8, the PLC continuously monitors key parameters, including the room temperature for the space heating and the storage temperatures at different layers of the heater, and also the electrical consumption. And additionally, the PLC regulates the operation of the electric heater or the radiator by adjusting its charging or discharging valves. And from the ICT perspectives, design develop the communication interface, define the communication content, and select the relevant ICT equipment, such as meters, routers, and edge computers have already been done. And like select the IT equipment to fulfill the following needs. The EMS will need constant access to both the live data and the historical data collected from the unit sensors. So it's decided to select a powerful industrial computer next to the unit to minimize the risk of any communication interruptions or data losses. And for IT security reasons, the local industrial PC will collect the data via a serious Modbus connection, as opposed to a PCP or IP connection, which would open the door to potential external instructions to the computer or PLC controlling the hardware. And to provide on-site internet access to the EMS, to access the weather forecasts and electricity prices, and to allow a remote connection to the industrial PC, we have chosen to use a 4G modern router accessible via a secure VPN connection. And this will allow for remote configuration and monitor the system. And also the build mobile units with each computing capacity to deploy the same solution on all project sites. And so in the figure 9, it's edge computing solutions we have already developed. And for testing a compact electrical thermal storage system, we also need to think about some risk analysis, such as the electrical safety, fire risk, ventilation and smoke, and also the structural integrity. And we have we have developed a test platform in DTU, and for this test platform, we will use the relevant dump load solutions to simulate both the space heating and domestic hot water, and we will also connect the radiators to the flexible house 3 to simulate the space heating. And there are some test points that we will monitor via the sensors during the tests. And we specify test cases, determine the specific test periods, and also the actuator action frequencies, identify controllable and non-controllable variables and parameters, prepare the relevant data, and set up a simulated test environment. And we also did some test cases. This is a system that using the flexible house 3 as the end user for space heating, and the PCM storage unit to store the heat and for space heating. And we use the genetic optimization to achieve the minimal operation cost, and also under the constraint of the indoor comfort, and we can achieve the minimum cost and guarantee the comfort level at a period of 10 days simulated. We also did some research work related to ZipLab heating system, which also include the district heating. And we can see from the results over a prediction horizon of 48 hours and a control interval of 60 minutes. From the top figure, we can see that the optimal charging schedule of the system could be achieved, and by using the EMS, and the energy stored and the energy demand are shown in the bottom figure. And finally, we will conclude that an intelligent EMS algorithm based on the MPC has been developed to optimize energy management for the Combiotis across the range of operating conditions and locations. And the algorithm features a generative presentation of modules for adaptability and optimality. Simulation-based results show it can be flexibly deployed in the EMS backend across various scenarios, significantly improving energy performance in cost reduction, flexibility management, and user comfort. And in addition to the basic modules, the EMS can also include other auxiliary modules such as data management, robustness module, visualization modules, and to improve its practicality, which will be selectively developed during the demonstration. And finally, the variance in locally available information across application sets means the current EMS requires manual configuration, automating the creation of matching files based on harmonized data streaming process. For example, linking to building automation protocols will be a key stepstone to enhance the EMS efficiency. And that's all. Thank you.
Thank you, Xin. Are there any immediate questions?
I can have one.
Yes.
If I can.
Yeah.
Okay, so thank you for the presentation. I have a particular question. Because this is broader topic, but I think mostly about the economical results from the, let's say, the forecasts and so on. Did you make some let's say, test to find the error of the prediction, for example, between the optimal operation of the storage and the results of, let's say, the forecasts and predictions. So maybe you can comment on that, how these two optimal solution and real solution from EMS are different.
You mean some test results, right?
Yes, maybe. I don't know if you test that if you have the real cases, but I just wonder how much the outcome. But for example, when we have the dynamic prices, so how much the outcome from the EMS will differ from the optimal solution. For example, when we have the full knowledge of the water demand and so on.
Yeah, because the system is still underdeveloped. So now we only build the test plan, test platform, and we still how to say, we just build each component now, like the EMS system and also the whole system platform, but we still not connect all things together to run the test. So we will still wait for the music system and then do the test later.
Okay, thank you very much for the comment.
So we only have some results from the simulation parts yet.
Okay, thank you.
But we will do this in the future and maybe show in next workshop.
Thank you.
The last session is devoted to the demonstration. So it will be less technical to finish this workshop. I will speak about the demonstration and only the demonstration of the music prototype, so the PCM storage. So the demonstration, in a large definition of demonstration, the main objective are the manufacturing of the prototype, its scientific characterization, and the demonstration. And we have two types of demonstration: a test in control environment and in test in real environment. Just a reminder of the storage and a reminder of the prototype, the complete prototype. One first element which makes the demonstration not so easy is that this demonstration is a cooperative demonstration, which is quite obvious in European project, but it implies a lot of interfaces. So, for example, what you can see here is a typical view or typical view of the demonstration. And so here you can see the prototype in orange, something like orange. You can see the prototype, and this prototype is made on the design of the CEA. Then we have a first interface and first work between CEA and another partner, who is Delaunay. Delaunay is the boiler maker. So we make with Delaunay the transformation of the paper study to the final, the paper design to the final design and to the manufacturing. At the same time, all the instrumentation put inside the storage is installed by CEA. So that means we have a lot of interfaces. Then the prototype is filled by CEA at CEA, and then the prototype is shipped to the demo site. On the demo site, the demo site owner or responsible will be responsible for the electricity, for its own demo site in terms of engineering, components, and so piping, in terms of, and we have a last interface, which is the EMS, the PLC EMS, just presented before by he. And so this part is made by DTU. And so that means that we have interfaces during the manufacturing. We have interfaces between the prototype and the demo site. We have interfaces between the EMS and the prototype, and between the EMS and the demo site. And each of these parts is made by different partners. So it's not so easy. Just now, the different regarding the different prototypes of PCM storage, we have 4 different prototypes: 1 for the CEA in Grenoble for the scientific and characterization, and 3 for 3 different real demo sites. And the instrumentation is not the same for all these prototypes. Basically, we have for CEA a prototype with much more instrumentation because we are performing the scientific characterization, and for the demonstration site we have prototype with less information. Basically, for example, for the scientific characterization we have more than 120 thermocouples inside the prototype, and we have only 31 thermocouples for the other demo site. For the other demo sites, thermocouples are mainly used for the calculation of the state of charge, the regulation of the internal heater, and the safety of the internal heater. For the scientific characterization, we have the same quantity of thermocouples for the same with the same objective, but we have also thermocouple inside at different position in the tube bundle. This is what we can see here. This is the illustration of the instrumentation for the scientific characterization. And so each point, for example, corresponds to a thermocouples. And we have this situation at different levels. We have 5 different levels, 5 different measurement planes on the height of the storage. And so we have thermocouple inside the fluid, the water. We have thermocouples in the tube bundle in the PCM, in the fins, but far from the tube in the free PCM region. We have thermocouples for the calculation of the state of charge. We have thermocouples for the regulation, and we have thermocouples near the tank wall, because near the tank wall we have, as you can see here, due to the geometric configuration of the tube bundle, we may have some important or higher thickness of free PCM. In parallel, and mainly due to the 3 passes fluid flow, we put some thermocouple inside the convex end at the bottom and at the top. And so, for example, for the bottom convex end, we measure the temperature inside the inner convex end, and we measure temperature inside the outer convex end. The objective is to obtain local temperature value to have an idea of the radial distribution and the azimuthal distribution also. We will have a lot of information to characterize at the end of the project, a lot of information to characterize the behavior and to characterize the innovation put inside the PCM storage. Now, looking at the demonstration sites. As I said, the first one is not considered by European Commission as a real demo site. This is a site for characterization. It is in France, in Grenoble. This is a fully academic test loop, which is called Smart Grid. And it will be the reference case for the performances, since we will use the prototype with the most important quantity of thermocouple inside. Then we will send a prototype to DTU. I will present later the demo site in details. This is a representative houses installation. Such installation has been already used in a lot of previous projects to test different storages, different way to operate such installation. So this is an installation which is clearly made for such demonstration. We will test only for the space heating, And since DTU is responsible for the development of the EMS, this demonstration will also be the reference case for the EMS PLC and the TES control. Then we have the Chambéry site in France. This is more or less the same kind of demonstration site as the one of DTU, which has already similarly already been used in numerous previous projects to test, for example, the insulation, to test the material used for the construction. And we have the final site, which is the real site in real operation with real people living in it. So a little, some more detailed information about each demo site. Here you can see some picture of the demo sites from the outside, from the inside. This is a real house, in fact, used for the demonstration. And I'm not sure it is always the case, but previously it has been also used to for people who visit, for example, for invited student or for invited professor to live near the campus of DTU. So it is in fact it is a real house, well instrumented. So what you can see also on this picture, this is the location of the demo house, and this is the location of the heat substation. Basically, all the control of what will happen inside the demo house will be made in this substation, and the prototype of music will be also included in this substation and controlled from this substation. So at DTU, we will send a very complete version of the prototype. This prototype will be plugged to the space heating circuit of the demo house. And as I said, this is a very complete version of the prototype with some measurements of the flow rate, some measurements of pressure, with a lot of safety components. And we have also the backup here for the internal heating. So this branch is devoted to the external heating in case of failure or malfunction of the internal heater. Looking at the Polish demo site, this is a real house. First, you can see on this picture where the prototype was supposed to be installed, but since a few weeks, we changed. Sorry, we changed the location because it was quite complicated to install the prototype in such small space. So the prototype will be installed, in fact, here in the garage. The prototype will be also installed in a more complicated configuration because this house is already equipped with a gas boiler here. This house is already equipped with a thermodynamic heater for the production of hot water. So that means it is a water tank coupled with a heat pump. They have already PV on the roof, and PV is electrically PV is used for the heat pump. And PV is also sent to the network. PV is used inside the house, but the gas boiler is also used in the water tank in case of backup, in case of really cold condition in winter. And so the integration is not easy. And the integration chosen is based on the fact that we will install the PCM prototype. We will keep the existing water tank as a backup in parallel, just to be sure that if we have any issue with the new PCM storage, people living in the house have a backup to have hot water. And so that means that the operation of the storage tank should also include a backup operation mode, just in case it's not working properly. Okay, and the final site is the one from CA in France. It is close to, in principle, it is close to the one of DTU, but in less developed and smaller, because we have only a small network of 4 different houses. So it's quite smaller than the one developed and studied at DTU. But for the one of DTU, everything can be made inside. And to go more in details, we have the prototype here. As you can see, there's no more backup for the INES prototype. It will be already the case for the Polish demonstration. There's no backup. We consider that it will work. And on this part, you can see the PNID of the INES demo site, and we choose to test either the production of hot water here, and to test also space heating using the floor heating. In parallel, which is also important, is to make a link between this demonstration and what has been defined in the beginning of the project and presented in the session 1. So I mean the use cases, the application scenarios. And the application scenarios are based on electrical use case, on thermal end use, and some functionality provided by the system. Just I reminded here the different scenario. The first one is based on the reduction of the costs based on differences in the price of electricity. The second one, the second scenario is focused on the reduction of grid load using the storage flexibility. And the third one is focused on the optimization on the use of local renewable energy, in this case PV. And so just to give you some information about the different demo sites, so you can see for each demo site which kind of electricity, which kind of use of TES, and which kind of thermal use has been considered. For DTU, the electricity will come from the grid, and so that means that we will simulate some specific tariff. So it will be just a simulation. The storage will be used for the reduction of the cost and reduction of the peak load of the grid. And we will perform just space heating between temperature of 45 and 55, and the flow rate equal to 13 liters per minute. On IO, which is clearly the most complicated demonstration, the electricity will come from the grid and the PV panels. So that means the first, it will add an additional layer of complexity to know what to do with the PV, the electricity coming from the PV. The storage will be used to optimize the electricity coming from the PV. The latest news from the demo site is that they want, or they will increase the PV they have on the roof. So that means that this consideration of optimization of renewable energy will be even more important. And we will only use the storage for production of domestic hot water. One point that will be clearly complicated is, as I said before, is that we will keep the existing water tank, and this water tank has to be will be considered as a backup. So that means that this water tank has to be always fully functional and fully operational. So that means that the use of the electricity coming from the PV and from the grid has to be divided between the existing water tank and the PCM storage. So which is an additional level of complexity. At CEA in INES, the electricity will come from the grid, we will simulate some specific tariff, and we will use it for the storage for the cost reduction and the peak load reduction, and we will perform domestic hot water and space heating. The space heating will be made, it will be interesting because it will be made with different consideration compared to the DTU case. DTU case will be based on radiator, and CEA INES case will be based on the flue heating. So the temperature condition will be 30 and 35 Celsius degrees, and the flow rate will be lower also. And just to summarize, to summarize and to give some elements in terms of planning duration. So at CEA Grenoble, we will perform some scientific characterization. We will perform an evaluation of the performance. We will validate the calculation of the, we will validate the internal charge and validate the 3-pass hydraulic pattern. We will consider internal and external charge. In parallel, there's no PLC. It is more or less a fully manual installation. So there's no PLC, no EMS. It is only scientific calculation. And we plan to start, the planning is more or less an issue in the fact that we have a lot of problems. So we postpone a lot of elements, but it's now planned to start in April for 3 months. At DTU, the main objective, one of the main objectives is the proof of concept in a relevant environment, and one of the major objectives is the validation of the EMS. So they will test internal and external charge. The prototype will be automatically controlled using a DTU PLC, and we will have the DTU EMS. The EMS at DTU will be the most intelligent for that of all the demonstration. It will start in April for 3 to 4 months. Just to give you information, as I said, these two first prototypes for Grenoble and DTU are currently under manufacturing. The tank is almost finished, the instrumentation is almost finished, the skid are currently manufactured, and we expect that it will be finished in mid-March. Then they are going to France to be filled. Then we are going, the filling in PCM will take normally 1 day maximum, and then they are directly sent to DTU. At CEA INES, this is the same objective, POC in relevant environments, only with internal charge, with CEA PLC, but the EMS is provided by DTU, and it will be a medium to high level of intelligence. The test will start in May for 5 to 6 months. And at EO, this is a proof of concept in real operation with only the internal charge, with a PLC from DTU and a lot of safety rules, and with a EMS provided by DTU. And it has been decided that this EMS is first will be based on very simple rule, with the first objective of meeting the heat load, because before doing anything intelligent, it is quite important to have something operational and functional. It will start in May also, with for a duration of 5 to 6 months. And just keep in mind that basically, so that means that the test will end at the end of the project, because the project will end in end of October. And that's all for me. If you have any question, any comments.
Yeah, there is a question. Go ahead, Gilles.
Yes, thank you for the last part of your presentation. Just to be sure, the auxiliary heater for each storage tank with PCM is electricity. inside
Yes.
the tank. Okay, all the
Yes.
time. Okay,
Yep.
okay. You don't have both charging and discharging with water. No, because it's electricity. Your auxiliary heater. It's only it's only discharging. In fact, when you use water, it's always discharging. It's not both charging and discharging with water. You never consider this option.
I don't really understand.
Yes, sorry. For all the solutions you consider, you always have electricity for charging hot water in your tank.
Yes.
Okay, all the time. Okay.
Yes.
You have never considered the case you use hot water to charge the tank.
It can be made at CA Grenoble. It can be made at CA Grenoble because basically the test loop used to do that is equipped with an electrical heater.
Mm-hmm.
And yes, it can be made at CA Grenoble and DTU. Just if we consider DTU, the main way to make the charge is internal heater placed in the tube. The backup is external heater, but the external heater means that we heat water and then the charge is made by this heated water. At CA Grenoble, we have these two solutions and we have another solution by using a more powerful heater. So that means we will be able to perform a kind of classical charge by providing the right level of temperature at the inlet.
Yes,
I'm not sure that I'm quite clear. The external heater is quite small. It is 3 kilowatts. So that means that the charge is made by multiple paths of water inside the storage.
Okay. Okay, thank you. Did you try to compare your case with PCM, your tank with PCM, with the same solution but with water? And what is the reduction of volume? Did you try to compare the reduction of volume? Because the interest globally is the reduction of volume, or
this
is
is
there
a very
any
good question, and this is a quite logical question. And the most frankly answer is that just at residential scale, it's difficult to see a real interest at the moment of using PCM storage, for example, for producing domestic hot water, because classical water tank will be quite less expensive in any case. Just what has been highlighted during the project is that, for example, in Europe, it will be complicated, but it seems that, for example, in China, the concept of static water for domestic hot water is not really appreciated. And in this case, PCM storage is clearly interesting because the quantity of static water inside because this is not a static water tank, this is a producing element. This is an element producing hot water. This is different. But frankly speaking, if you want to compare the capacity, perhaps, but perhaps you have some advantages in terms of capacity. But if you were to compare the simplicity and the costs with water tank, the PCM storage will lost. And another conclusion of the project is that such a storage become more interesting if you are no more considering a single house, but if you are considering aggregated or common storage for example, for building or for neighborhood.
Okay, if you increase the size, it's becoming more interesting. Okay. Okay, thank you. Thank you for all the presentation. It was very interesting.
Thank you.
And thank you very much.
It
We
will
already
be available. If I'm not wrong, Christina, it will be available on the CombioTest website.
okay.
Yes.
Can you put the link in the chat? Yeah. Conversation.
Yeah, you have the link to.
Okay, I can see it.
I can put it. You have the link to our LinkedIn page where we will be posting updates on the project, on the results, whenever we will be achieving a milestone. And I can also put the link to the website. And on our page called Training Activities, you will see the tutorials that we have prepared and delivered during the workshop. So you will have access to the PowerPoint presentation if you want to review them again.
And basically, the workshop is a very light version of the tutorial.
Yeah, so in the tutorial, you'll find more extensive and more comprehensive explanations on all of these topics. So yeah, I think that if everything is clear, we can declare the meeting closed. And thank you to everyone for attending, for sharing your questions and insights. And please follow our LinkedIn page and website for more updates on how we progress on the project.
Okay, pleasure.
Thank you very much.
Thank you. Thank you.
Thank you very
See
much.
you.
Have a
Bye-bye.
nice
Bye-bye.
day.
Thank you. Bye.
Bye-bye.
Bye.